learners, welcome back to the System Design playlist. This is video 5.2. In the previous video, we discussed about monolithic architecture, what it is, the properties and characteristics, what limits does it pose, and what eventually leads us to actually shift to a distributed system. The agenda of today's video is to learn about a distributed system, what actually changes when we cater to a distributed system, the benefits of a distributed system, and the hidden costs or the trade-offs of a distributed system. So let's move to our first topic. In our last video, we have pushed our monolithic architecture to its breaking point. That is horizontal scaling. Basically, in a monolithic architecture, you have one machine who is performing all the work, right? Now, if I keep increasing CPU and memory for this one machine, because my user base is going to continuously grow. I have a continuously growing user base. So if I keep increasing my CPU and memory according to my user base, it will work for some time. But after some time, when my user base hits a certain limit and my CPU and memory cannot go beyond that because you have certain physical limits, right? You cannot just keep increasing a CPU and memory to an infinity, right? So all of the users in a monolith are hitting the same server. You see, for all types of jobs, the same server has to handle all the requests. To fix this, we don't just buy a bigger server. We fundamentally change the architecture and we move to a distributed system. Now, what is different in a distributed system is that instead of one giant machine doing everything, your application is now split across multiple independent machines. And these machines communicate over a network to achieve one single goal. To the user, it looks like just one application. It will still look like one application, but under the hood, it is an orchestra of different servers, right? So different servers are going to perform different jobs, and that is how your requests are going to be directed, as you can see in the diagram as well. Now, let us try to understand distributed systems with a metaphorical example. We'll take the example of a restaurant. I'm sure all of you have been to a restaurant. If I have to describe a monolith in terms of a restaurant, a monolith will look like a restaurant where there is just one chef who is doing everything, right? This is the person taking orders, this is the person cooking the dishes, also washing the dishes. Whereas a distributed system is like a specialized kitchen. What do I mean by that? A distributed system is like a specialized kitchen. You have a manager at the front who is taking all the orders, right? You have a grill station, you have a separate salad station, and you have a separate person who's washing the dishes. Basically, different work has been divided into different people, but all of them are towards one single goal, that is, they have to work on the restaurant sales, right? So basically, all of these people are working on operations of the restaurant. This is how our distributed system actually works. From a word I view, this is how you can imagine it to be. You have different servers who will independently perform different tasks on a single goal, right? But they're independent, so there's no load on just one single person in this example of a restaurant. Similarly, there is no load on one single server or one single machine to perform all of the tasks of your whole application, right? So I'm sure you understand that converting our monolith to a distributed system will definitely affect our architecture. So let us come back to our architecture. We had earlier seen that in our architecture there is a user and there's a server and there's a database, right? And the user will send requests, the server will fetch data from the database, and it will send response back to the user, right? This was the simple design of an architecture we have seen. Now that we have shifted to a distributed system, you will have multiple servers, right? Now these servers are connected to your database, or if you have multiple databases as well, we'll come to that later. And these multiple servers are now not directly receiving your request, the user's request. Now there is a load balancer in between. If I have to take you from the restaurant example, this manager is taking your orders, right? This manager you see here, who's taking your orders, this is exactly like the load balancer. Now let us first understand what a load balancer is. We have seen that there is a user and the user sends requests to the server who fetches data from the database and returns response back to the user, right? Pretty simple client server architecture we have seen. Now in a distributed system, you don't just have one single server, you have multiple servers, right? So let's say, for example, I'm taking three servers, right? S1, S2, S3 are my three servers and I have a user U. Now, my distributed system has different servers, so it can handle traffic better, right? And it can cater to a larger user base, right? But now, if I am a user and I am sending a request, I want some data, I want some file, I want to watch a video, whatever. I'm sending a request to this application, and this application in the background has these multiple servers. Now, I need you to tell me, if I'm sending a request, will my request go to server 1, server 2, or server 3? Where will it go? This is where your load balancer comes, right? So load balancer is a layer that will come between the user and the server. What is the load balancer efficiently doing is that For example, let's just draw this again. I have a user and I have 3 servers, right? And in the middle, I have a load balancer. Okay, what the load balancer does is it will take the request from the user, right, and direct it to the available server, right? Now there are multiple algorithms in which load balancer can direct your request to the server. Basically, load balancer is going to check which servers are available and send requests to the server. Basically, I am user 1. Let's say I'm user 1 and I have sent a request. It goes to the load balancer. The load balancer sends it to server 1, right? Then server 1 goes to the database and then retrieves the data that I want and sends me back the response, which comes back to me through the load balancer again. This is my response. Okay. Now, for example, there are multiple users, right? So there is like, let's say there are n users. I have n users. So there will be n requests as well. Now let's say first request is directed to S1. S1 is busy. Second request is directed to S2. Now S2 is busy. Third request is directed to S3. Now S3 is busy. Now if there's a fourth user, what will happen to the fourth user? That user will have to wait a bit. And for example, let's say the server 1 has now completed this job, right? The user 1's job. Then the user 4's request will go to the server 1. This is user 4's request. And this was user 2 and this was user 3. User 1 request is already sent. Response is sent. Okay. Now this example that I told you, this is an algorithm which is called round robin. Right. So basically there are multiple such algorithms which help the load balancer decide which server should get which request next. Right. So basically to understand what a load balancer is the one who will decide which server will get which request, because you are one user and there are multiple servers. So which part of the system decides where your request goes, to which server your request goes, that is the load balancer. Coming back to our architecture. So I hope you understand this architecture better now. So a load balancer, it will look at the incoming traffic and it will route it to an available server, because we have multiple servers in our system now, since it is a distributed system, right? If one server goes down, this is also one very important point about distributed system, that I have multiple servers, right? And I have a load balancer who is redirecting traffic everywhere. So if one server of this goes down, for example, let's say S1 goes down, right? So then the load balancer will redirect these requests to either S2 or S3. So basically, if a server goes down, the user will not face any problem and the load balancer will redirect all the requests until S1 is back again, right? That is how a distributed system is actually very helpful when it comes to servers getting down or even databases going down, right? That is how it is helpful for the user and the user experience. Now let us come to what actually has changes, right? What has actually changed? When you make these shifts, like from going to a monolith to a distributed system, there are three massive things that are going to change for you as an engineer. First of all, your multiple servers are now handling your traffic, right? So you are not constrained with one single machine. You're not constrained with the limits, the physical limits of one single machine, the hardware limits of one single machine, right? You have separation of concerns. What does that mean? That you have broken the code apart. In a monolith, for example, there is one service and let's say there are 10 services you have, right? In a monolith, maybe all of the code of the 10 services was together. Now, since I have distributed my services into different independent ones, your code will lie on different servers given the different jobs they are doing, right? So basically, if I tell you, let's say a user login, right? There is a code for user login, and let's say there is a code for image upload. Now, both this piece of code is now going to lie independently on different servers. That is how your separation of concerns is happening, right? Because both this code is not lying on the same machine. In fact, it is on different servers. This may be on server 1, this may be on server 3, right? Depending on whatever the job of the server is given. Now, the third change is distributed data. Your data is now replicated and partitioned across multiple machines. When we will study about database, we will also study about data replication and sharding, because you have multiple servers, right? So every server, you can connect all the servers back to one single database as well, or you can have multiple databases as well. Now, when we'll study database, we'll go into much more detail, but this is also one very massive change that happens when you move to a distributed system. Right? Now, what are the benefits of a distributed system? We saw a drawback in our previous video, if you remember. A drawback of monolith was that there is a single point of failure. Because in a monolith, I have one server and I have one database and I have one communication network. If any of this goes down, my entire application is going to go down. And Obviously, that is not a very good user experience, right? So the benefits is the massive scale, first of all. Because see, going to a distributed system from Monolith is a tedious task and you have to change a lot of things. So why should you even, go through all of this trouble? Because it unlocks massive scale for you. See, there is no single point of failure, right? For example, if you have an AWS server, right? You're working, your app is hosted on AWS. If AWS data center loses power, your app still stays online because the other servers, even if one server goes down, the other servers, they're going to pick up the slack, right? So there is a single point of failure and your app will keep running even if there is one discrepancy somewhere, right? And again, horizontal scaling, coming back to horizontal scaling, we saw that there is a lot of vertical scaling that goes into monolithic architecture. Okay, maybe I realized when we were studying this, here, did I say horizontal scaling? This is vertical scaling. When you're increasing your CPU and memory to a limit so that you can cater to more and more users on one single server, you're increasing CPU, increasing memory. This is called vertical scaling, right? And coming to horizontal scaling is what we have actually done with our servers, right? I had one server, now I had expanded it into more than one servers, right? This is horizontal scaling, basically. And when you are working with a distributed system, you have the possibility of infinite horizontal scaling. For example, you have 10 servers right now on a distributed system, and your user base grows so much that even 10 servers can't handle it. Okay, you can just spin up 5 more servers and they will do your job. Now, obviously, in real world scenarios, you have to look at the cost, you have to look at viability, and a lot of other things. But given you have the resources, our systems are pretty capable of handling that big of a user base as well. Now, the final benefit that I'd like to talk about is developer velocity. You see, in a distributed system, your different engineering teams, they can work on the messaging service. For example, you have a messaging service and you have a payment service, right? So your different teams can work on different services simultaneously. Very important, simultaneously, without breaking each other's code. Because if I have just one piece of code where everything is there, right? Now different teams are going to work on different things, and maybe somebody changed something right here, somebody overwritten that and changed something there. This is how you're actually breaking your code, right? Now, given you have a distributed system, you have more people, that means your app has grown. So you hired more engineers. So it will be easy for them to actually maintain your application because now the code is not on a single server or there's just not one single piece of code. In fact, there's a lot of sections to it. And you've divided it into different servers according to the work or the job they're doing. Now, given this distribution, the velocity of a developer, that is how fast the maintenance is going to happen, or if you need to update something, how fast that is going to happen, it is going to be increased much more than it will be in a monolith, right? Now, for example, I have one application and I have to scale one service, right? I don't want to scale everything. In a monolith, this is also a problem that because I have a single machine, now I want to scale one single service of my application, I have to scale the entire machine. I have to put CPU memory to the whole server, right? Because it is the one doing all the job, right? So in case I want to scale even just one single service, I'll have to vertically upgrade the whole machine. Now, obviously, you can imagine the cost, the effort that will take to do that. Now, if I have multiple servers doing multiple jobs, right? Job one, job two, job three, and if I have to scale job three, I don't need to look at job one, job two. They're doing well on their own, right? They're okay, fine. I will scale job three, right? So this is how distributed systems are also going to provide you an advantage and very good flexibility when it comes to scale. Now we have talked about the benefits, and obviously everything that has certain pros has cons as well. So the distributed system also holds hidden costs, right? See, so this is the most important lesson in system design. In system design, you see there are no solutions. You will encounter a lot of problems, but there are no solutions in system design. There are only trade-offs. Basically, you have to choose one thing over the other. You have to maybe compromise for one thing. Because you see, distributed systems are vastly more complex. Because your services, instead of being on one single machine, now your services are distributed on multiple machines. Isn't it? Service 1, service 2, service 3. Right? So they have to talk over the internet because now, given your services are distributed between machines, but finally you are one single application, right? And there can be a lot of cases where the services have to talk to each other as well, isn't it? Maybe service one wants to talk to service three, or the other way around, right? Now, how do they do that? Service one is talking to service three or to any other service, let's say service N, to the internet, right? They are connected to the internet. That is how they are communicating. But for example, the connection is dropped, right? For a few seconds, the connection is dropped. So then what will you do? The server will not be able to communicate with the server N properly, right? Because of this complex system, we have to think about internet being dropped, right? Also, for example, let me take a data example. I have a database. Let's say I have a table, okay? And there is a server A who changed something in the table, right? Server A came and server A has changed something. Let's say we will just put here, right? So server A has changed something in the table. Now, since you have changed something in the table, now you have multiple servers, right? There is server A and then there is server B and there are multiple servers. Now server A changed something in the database, right? Now server B should know about this because I am a user. For example, the load balancer. The load balancer, it takes my request and server A is busy at the moment, right? So it takes my request back to server B. And server B does not have access to this changed information. Will I get the right information? No, I will get the wrong information. So server A, whatever changes it has made, server B should know that. So that is has to sync, right? But suddenly, if server B crashed, server A has updated the database and server B has crashed before it has gotten the memo of this updated database. What will happen? You will have to debug this error, right? And if you have 20 different servers, you will have to debug a user error and it will mean tracing logs across 20 different servers instead of just one, right? Related to monolith. So, given these problems, let us come to a golden rule. So there is a golden rule, and the golden rule says you start from a monolith. Always and always, you start from a monolith, right? You may think, okay, my app is going to cater so many people, and my app has a potential to be able to be, be of interest of a lot of users. But when you start with a monolith, okay? Only when you hit your limits. And when I say hitting your limit means that you have hit your limits of vertical scaling. You have hit limits of your hardware, the physical limits of your system. And the CPU memory, it cannot be infinitely increased. So once you've hit those limits, but your user base is big enough that it cannot be catered by this monolith that you already have exist, and you have hit the limits. Now you need to change something. That is when you come to distributed system. Okay, here this is the point when we will shift to a distributed system. You know, introduce a lot of complexity to your overall system. So only when you actually need it, shift to it. Don't do it from the very start. Always start from monolith. When it hits the limits, physical and hardware limits, that is when you shift to your distributed system. Right? Migration to a distributed system is basically to solve your specific scaling problems, majority. Right? Now you've understood this journey. You know why monolithic systems eventually break and how distributed systems are solving those exact bottlenecks by dividing the work. But I mentioned a moment ago that in a distributed system, network failures are inevitable, right? Network can fail, a lot of things can fail because you don't have a single point of failure, but you have many points of failure. The problem is that in a monolith, if I have a single point of failure, my entire app is going down. In my distributed system, since I have multiple machines working, even if one machine fails, that's okay. My traffic can be redirected to the other machines that are still working, which is great. It improves my user experience and it improves the response time as well. Good for me, good for them. But in a distributed system, I'm facing that complexity of handling and maintain those multiple machines, and when they're going down and how to bring them back, you have to do that maintenance. So it is inevitable that failure is going to happen. You cannot have perfect consistency, availability, and partition tolerance all at the same time. Partition tolerance is basically fault tolerance. We've discussed this in the previous videos in the same playlist, right? So there are three things that we look at here. One is consistency, one is availability, and then there is a fault tolerance or partition tolerance. So you have to make a choice. You cannot get all of these three at the same time, right? That my system is 100% consistent, 100% available, and 100% fault tolerant as well. You cannot, that is not possible because failures are inevitable and no system is 100% the best. You have to work on your requirements. What are the requirements of your app? What can you afford to lose and what can you not afford to lose in any way? That is how you decide what you will compromise and what you will prioritize. And the mathematical rule that will govern this choice of yours, that is called the CAP theorem. CAP stands for, again, consistency, availability, and partition tolerance. That is your fault tolerance. So that is what we'll cover in the next video. What is the CAP theorem? We'll try to understand that and how do you actually make a choice in which how your system and the requirements of your system, how you govern the choice of understanding what you will compromise and what you will prioritize based on the CAP theorem in the next video. Till then, stay tuned. Happy learning.